After completing a BA and DPhil in Metallurgy and Science of Materials at the University of Oxford, Dr. Ian Baker joined the faculty of the Thayer School of Engineering at Dartmouth College in 1982, where he is currently the Sherman Fairchild Professor of Engineering. He was chair of engineering science from the 1996 to the 2000, MS and PhD program director from the 2000 to the 2005, director of the NIST funded Center for Nanomaterials Research at Dartmouth from the 2002 to 2005, director of the NIH funded Center for Cancer Nanotechnology Excellence on Magnetic Hyperthermia from the 2011 to 2016. Senior Associate Dean for Academic Affairs from the 2005 to 2019, and he's currently the Senior Associate Dean for Research and Graduate Education. Dr. Baker was a CASE at NASA Cooperative Aerospace R&D Fellow at NASA Lewis Research Center, Cleveland in summer end 2005 to 2006, and Principal Research Metallurgist Sherritt Gordon in Alberta in the 1991. Dr. Baker is a chair in engineer and a fellow of ASM International, TMS, MRS, IIM, and AAAS. He has been the editor-in-chief of Materials Characterization Journal since 2008, and he is on the editorial board of several journals. He has published over 400 papers, and he has given over 400 presentations around the world at different conferences, universities, and to industry. He has organized several conferences on snow film, ice, and intermetallic compounds. With that, we are glad to receive today to Dr. Ian Baker, and I ask you for please welcome him to this talk. Please, Dr. Baker, you can start your presentation. Thank you so much.
Okay, thank you for that introduction, and thank you for inviting me. I have given over 400 talks, but I've never given a talk on Zoom before, so this is a new experience for me. So I'm going to talk about high-entropy iron, nickel, manganese, aluminum, chromium alloys that we've been working on for many years with support from the National Science Foundation, the Department of Energy, and also the Engineering School. I'd like to acknowledge people who've worked with this on me recently, a number of people at Dartmouth, a number of people at Argonne National Lab, including C. Chen, who's a former student of mine, people at Oak Ridge National Lab, and somebody at FEI, which is a company that makes electron microscopes. So let me start out with the definition of high-entropy alloys. The single-phase alloys, which have from 5 to 35 atomic percent of at least 5 different elements or components, and by components, we mean they could be oxides instead. The originators of high-entropy alloys were Brian Cantor and J.W. Yeh, and it was actually J.W. Yeh who came up with the name high-entropy alloys. And the idea was that for high-entropy alloy, the configurational entropy offsets the entropy of intermetallic formation so that you end up with a single-phase material. And the idea also was that they would have 4 attributes. In addition to the high entropy, they would have severe lattice distortion, which would help with strength, sluggish diffusion, and so-called cocktail effect, which meant the properties would be greater than the rule of mixtures. And I'm not sure in many cases, many of those attributes actually occur. I'd also like to define multiple principal component alloys, which really have the same definition, except that not necessarily single phase in this case. And the first multiple principal component alloys were really alnico alloys. Alnicos were invented in the 1930s. Although it sounds like they're an iron nickel cobalt alloy, they're really an iron-based alloy with those elements in. And they consist of B2 and BCC phases. B2 is ordered body center qubit. And in the 1950s, Alnico 8 and Alnico 9 were invented. And if you look at the compositions, they were clearly multiple principal component alloys. So they've been around for a long time. We started work on structural materials in around 2004, when we produced some spinol alloys with a really fine microstructure, very strong, up to 2300 MPa, very little ductility. So just a brief overview of what we've done in my lab. So we've really looked at 4 types of microstructures. So we've looked at these ultrafine microstructures, which are formed by spinodal decomposition. Here's an image of one here. And these tend to be somewhat equiatomic, iron, nickel, manganese, aluminum, and they consist of B2 and BCC phases, or L2-1, which is a further order in the L2 of the B2 structure, shown down here, L2-1 plus B2. They turn out to be incredibly strong, but quite brittle. Then we actually looked at some alloys where we lowered the aluminum content, and we ended up with an FCC and B2 structure in plate form, with the orientation relationship shown here. They also turned out to be relatively strong, but also not very ductile. Then when we lowered the aluminum content further, we ended up with a lamella structure that was formed by eutectic reaction, again, which consists of FCC and B2 lamellae in this case, with a Kurdjimov-Sachs relationship between the two. And then finally, when we lowered the aluminum content further still and added chromium, we ended up with single phase FCC alloy that we'll also looked at in the carbon dope form. And what I'm going to talk about in here for the rest of the talk is just these last 2 types of alloys here, and I'm going to start out with a single phase material. So we somewhat quite often refer to these as high strength stainless steels because they have very similar properties to stainless steels, but you can see the composition that we're looking at here has got also manganese and aluminum and a lot less chromium than stainless steel. So this is a typical ASCAS material with a grain size of over 100 microns. And we've actually looked at these with different amounts of carbon. And so this is X-ray diffraction data from the argon synchrotron. And the 0 means with no carbon, 1.1 means we've got 1.1 atomic percent carbon. And you can see for all of these, we've got the same diffraction peaks, and they're all face center cubic. And if you look at the lattice parameter as a function of carbon content, you can see it's actually pretty linear, and so is the lattice strain, indicating that the carbon is really in solution. And we can also look at the arrangement of the atoms in the structure using atom probe tomography. So for those of you not familiar with this technique, use what's called a local electrode atom probe, where we make a thin needle of our material, put that in front of a local electrode with a very high electric field on it. Then we pulse the field, and this strips off atoms from the surface of this needle. These travel through the electrode and impinge on this microchannel plate. From the position they hit on the microchannel plate, you can figure out where they came from the specimen, and the time they took to get there, you can use to figure out what the element actually was. And this is what one of those needles looks like, one of our alloys. And this is the sort of results we've got. So this shows the different atoms in the microstructure, and this Pearson coefficient up here shows you whether the alloy is random or not. And so if this Pearson coefficient is close to 0, then you've got a pretty random alloy. And you can see, and that indeed is the case, that we've got a pretty much a random solid solution of the material. So we looked at mechanical properties, and the really intriguing thing about these materials, so this is a material without carbon, and when we add carbon to the material, you can see 2 things happen. One is the yield strength goes up, the other is the ductility goes up, the elongation, the failure goes up, which is an intriguing feature to get both an increase in strength and ductility. The other interesting thing is what happens to work hardening rate. So this is the material without carbon, and you can see the work hardening rate initially increases somewhat, and then it starts to decrease. Once you add carbon to material, 2 things happen. The work hardening rate increases more, and you continue work hardening up to a greater strain as well. So by the time you put 1.1 atomic percent carbon, you see a much greater work-hardening rate, and work-hardening continues to overstrain 30%. You can plot the yield strength as a function of carbon. Sorry about the fuzziness of this image. And you can see we've got a pretty much a linear relationship here, which is unusual because typically when you have solute strengthening, you've got a concentration to 1/2 or concentration to 2/3 relationship. And if you look at the strengthening we get from carbon, it's about 184 MPa per ton% carbon, which actually compares pretty well looking at other materials. So this is another common high-entropy alloy, and this is a quick steel. And you can see that the strengthening effect is greater for this material. We looked at dislocation structures, and this is the material without carbon at different strains. And you can see a pretty wavy sort of dislocation structure. And as you get to very high strains, you get dislocation cells forming and these dense dislocation walls. Once you add a little bit of carbon to the material, even the smallest amount we added, all of a sudden you start to get this much more planar slip in the material. And at very high strains, you get these microbands forming in the material. And you can see here, by the time you've added 1.1 ton% carbon, you've got a very planar slip structure, and these microbands aligned along 111 planes. And we think these microbands are the reason that we get both a high work-hardening rate and the high ductility. So we looked at the partial separations in this material. So these are choppy partials here, looked at using weak beam imaging. This is the undoped high-entropy alloy. This is with 0.07 ton% carbon. This is 1.1 ton% carbon. And you can see that the partial separations increase, so that stacking fault energy is going down. So that's one of the reasons why you get this much more planar slip, is that the dislocations are confined to the slip plane. So the difference between having no carbon and carbon in this material is that with no carbon, when you strain the material heavy, you get these dislocation cells, these dense dislocation walls, whereas in the carbon-containing material, you get a Taylor lattice of just randomly oriented dislocations, and these microbands which dominate the microstructure. The other interesting thing is the change in fracture when you add carbon. So this is the undoped material. See a typical dimple ductile type rupture. When you add carbon, you get more ductility, but you lose that. It looks more of a glassy fracture to the surface. So one of the things we've done with this particular alloy is to do some thermomechanical treatment. So we cold rolled it to a 70% reduction and then annealed it. And we did this actually for the undoped alloy and the one with the highest carbon content. And there's a couple of things I want to point out from these images. One is you can see that there's actually a number of precipitates that are formed in the alloys, and they look different at different temperatures. The other is that you can see the annealing conditions for the carbon doped alloy were actually higher than for the undoped alloy. So we annealed at high temperature, and that was because to recrystallize the carbon doped alloy required those higher temperatures, which is what you might expect if you had some solid like that. So looking at what we have after the typical anneal, for the undoped alloy, we had both phase center cubic and the second phase particles. They're labeled here as body center cubic, but in fact they're ordered body center cubic. And for the carbon doped alloy, which was actually annealed at higher temperatures, we've actually got some carbides forming in the material. This shows the carbon-free material. And you can see these particles all throughout here and an X-ray diffraction. If you look in the TEM at some of these particles, you can see one of these particles here, which corresponds to a B2 phase. And if you look at the chemistry, then the particle itself has much more nickel and aluminum in than the matrix, which is mostly iron and manganese with some chromium. Turning to the carbon doped alloy, you can see we can identify two different types of precipitates at this temperature of 1273 Kelvin. And if you look at the microstructure, you can see dark precipitates and light precipitates, which correspond to these two different kinds of carbides. If you go to a higher temperature, you only end up with the M7C3 type carbides in the structure. Just these dark ones are there after that. And you can again identify these in the TEM, these two different kinds of carbides, which were identified by electron diffraction. And we also did energy dispersive X-ray spectroscopy on them again, as shown here. If we look at those results, what you see for the carbides in the material is they have a lot of iron, manganese, and chromium, and very little aluminum and nickel because they're not strong carbide formers. Using again atom probe tomography, we looked at the grain boundaries, and what you find is after we've had this recrystallization processing, we've actually got an increase in manganese at the grain boundaries, a decrease in nickel, and an increase in carbon at the boundaries here. And you can actually see this on some of the images themselves where we've got excess carbon. So we looked at the mechanical properties of the material being crystallized, and the ones that we crystallized at different temperatures had different grain sizes. So this is the undoped high-entropy alloy, and this is the carbon doped. And you can see as you decrease the grain size in both cases, the yield strength increases, and so does the ultimate tensile strength, but the ductility decreases in both cases, as you might expect. This shows the strength then as a function of grain size, and as you decrease the grain size, the strength goes up again, which is typical sort of behavior, and the ductility goes down. Again, we looked at the dislocation structures in this material, and in the undoped high-entropy alloy, again, we just got these sort of wavy dislocations of the material leading to dislocation cells, and you can also see the B2 particles here where there's quite a lot of dislocations forming around those. In the high-entropy alloy, we did see one difference. For the larger grained material, we again saw dislocation structures exactly the same as in the as-cast material, where we got these microbands at high strains. But when we got down to 5 micron grain size, we no longer saw this microband structure in the material. So that's a slight difference as we get to very small grain sizes. So the grain boundaries must interfere with the microband formation in some way. If you look at the whole patch behavior, then you can see this linear relationship with the carbon doped material and undoped, and they look like they have different slopes to them. But you have to remember that when you're looking at these points here, the difference between them isn't simply the difference in grain size, but also is changing the precipitates in the material. And as we're forming carbides in the material, we're taking carbon out of solution. So if you look at this is the undoped alloy, and this is the doped alloy. We've got these different grain size materials. So in this one, we've got B2 particles forming after the thermomechanical treatment. And in the carbon doped alloy, we've got these different carbides forming. And so what we did was we actually looked at the precipitate diameters we got in each case and the precipitate volume fractions. And then what we could do is we could back out of using a calculation to back out contributions of the precipitates from the yield strength of the alloy. So this is the yield strength we measured. We could calculate what the precipitate contribution was, and then get a yield strength without precipitation strengthening to get what to replot the whole patch relationship. For the carbon doped material, not only do we have a precipitate strengthening, which is actually in some cases quite small, but we've also removed carbon from solution, which is a very large strengthening to material. So we've actually lost this strengthening from the carbon. So we've got strengthening from precipitates, but we've lost this. So we can recalculate the strengthening in the material when we take into account those two factors. So if we replot the yield strength as this reduced yield strength, where we take into account the precipitation and the change in carbides, and plot that as a function of grain size to -1/2, you can see now the whole patch relationship looks pretty similar to the two. And so the carbon doping doesn't do a lot to the whole patch relationship. And finally, on these materials at room temperature, you can see we've compared them here to the different kinds of steels in this so-called banana plot, where we've got elongation as a function of tensile strength for many different steels. And you can see these carbon doped high-entropy alloys actually have very good properties. You want to be up in the right-hand side here for the best properties. We also looked at the temperature dependence, only for the carbon doped alloy of the mechanical properties, and for two different grain sizes. And if we look at the yield strength, you can see as you go up in temperature, the yield strength goes down, which is what you'd expect. The yield strength actually goes down more rapidly for the fine grain size material. We may even be getting some grain boundary sliding at this temperature, that's why it's weaker. But interestingly, as you go from room temperature down to 77 Kelvin, there's a really dramatic increase, more than a factor 2 increase for the coarse grain material. So really quite dramatic, and you've got a strength here of over 1100 MPa for fine grain material. The ductility actually shows more complicated behavior. So for the fine grain material, the ductility broadly decreases with decreasing temperatures. So we get about 10% strain liquid nitrogen temperatures. Whereas the large grain material actually shows similar ductility, room temperature and 673 Kelvin, about 50% elongation. It decreases at high temperature, and as you go to 77 Kelvin, the ductility goes down to almost 0. So let me just summarize some of what I've told you there. So what we found is that we can get up to 1.1 atomic zinc carbon soluble in our asbest high-entropy alloy. That the change in lattice parameter increases linear with carbon content, and the yield strength also increases linear with carbon content and with the lattice strain as well. The work hardening rate increases with both the carbon content and strain, and the carbon increases the elongation of the alloy. It also changes the fracture mode from this dimple type rupture to a glassy fracture mode. And the carbon leads to this microband formation of large strains, which we think is the reason we get very good ductility and high work hardening rate. If we do thermomechanical processing or simply just annealing, we get second phase order body centered cubic particles forming or carbides at hard temp in the material. We should note that this material actually is stronger than a 304 stainless steel, which is the most common stainless steel. And the whole pitch strength is largely unaffected by carbon. And we get a very strong temperature dependence to the yield strength at low temperatures. So with that, let me turn to the rest of the talk is actually going to be about some microstructures and materials that we worked on prior to that high-entropy alloy. So we started out looking at this this composition here with 15 aluminum, which is has a B2 FCC structure, and then we did various things to it, like we added chromium, and you'll see why we did that initially. Then we looked at varying aluminum content. We looked at some thermomechanical processing. We looked at nitride material, titanium modification, and carbon doping of the material. And then I'll summarize what we found. So this is what the microstructure of this material looks like. This is a backscatter electron image where you can see the two phases. And this is a transmission electron micrograph. The diffraction patterns over here identify those two phases. The light phase is phase center cubic, and the dark phase is body center cubic. And you can see that the lamella spacing is maybe about half a micron, something like that. If you do X-ray spectroscopy from the two phases, what you find is the FCC phase is very rich in iron and manganese, and the B2 phase is rich in nickel and aluminum. If you look at the diffraction from the two phases together, we find that actually there's a Kurdyumov-Sachs relationship between them, which is often seen between BCC and FCC phases. If we do some lattice imaging from the material, we see these very nice lattices for the two and a very clean interface between them. And one of the things we found is there's no particular lattice distortion. All these planes line up very clearly. We did some calorimetry on this material, and we see a couple of peaks. So we see this peak here at about 1180 centigrade, and this we think corresponds to B2 to BCC transformation. And then we get a peak around 1237, which is melting the material. We've actually processed this material in several different ways. So we directionally solidified it. We slow cooled it after melting, and we quenched it after melting. And you can see there's quite a change in the microstructure. This actually, if you look at the scales here, are quite different. So this directionally solidified has quite a coarse scale, And over here, we've actually got quite a fine scale and a very unusual microstructure. And as you might expect, as you go to a finer microstructure, the hardness increases. We did some mechanical testing on those different microstructures, and the quench microstructure was actually quite brittle. So we didn't manage to get any ductility at all. The slow-cooled material had a strength of about 600 MPa, and the direction was solidified for about 450 megapascal. One of the interesting things when you deform this and you look at it in the TEM afterwards, what you find is that basically all the dislocation activity is in the FCC phase. And at these sort of strains, to fracture here, there's really little activity in the B2 phase. And the reason for that is we've done nano indentation on these two phases, and the B2 phase is actually about twice as hard as the space in the cubic phase. If you look at a cross-section of a specimen strain to failure, this is the directionally solidified material, in which the very large grains of material. You can see actually this is the FCC matrix, and these are the B2 grain. You can see the B2 grains actually fractured. It's almost like you've got a fiber composite with B2 fibers in an FCC matrix. If you look at ion magnification, you can see this sort of fracture behavior in the B2. We model this as a fiber composite. So one of the very interesting things about this is when we do tensile testing, if you look at the yield strength as a function of strain rate, there's no effective strain rate from the yield strength, but there's a really dramatic effect on the ductility. So at high strain rates, you can get about 10% elongation. As you go down to a slow strain rate, the ductility decreases down, so you can only get about 1% elongation. And the reason for this is likely to be this mechanism first suggested by C.T. Liu and co-workers for the environmental embrittlement of iron aluminide. That is that the water vapor attacks the aluminum, it forms aluminum oxide, and then releases atomic hydrogen. And this atomic hydrogen then diffuses into material. And if you're doing a high strain rate test, there isn't time for hydrogen to diffuse into on the crack tips. But if you're doing a slow strain rate test, then the hydrogen can diffuse in and lead to fracture. And in fact, this is the work we did quite a long time ago, looking at a similar sort of effect in iron aluminum. So these are 4 different alloys of iron 45 aluminum with different grain size and different boron contents. And this is the elongation as a function of strain rate. And you can see that at slow strain rates, we get very little ductility. And independent of what the grain size is or whether we have boron or not, we get about 2% elongation. When we strain at high strain rates, now we can actually get more ductility, and we can see the effect of these metallurgical parameters. So this alloy here, which has both boron and a fine grain size, gets more ductility than the other compositions. So one of the things we decided to do to try and fix this environmental effect was add chromium to the material. So this is the material we started out with no chromium, and these are different amounts of chromium going from 0.5 through 1, 2, 3, 4, 6 atomic percent, and 8 atomic percent. And by the time we get to 8 atomic percent, the microstructure has actually changed. We're up to 6 atomic percent chromium. It's essentially the same lamellar spacing and structure as the material without chromium. We looked in the TEM at these microstructures, and again confirmed the B2 and FCC. And if you look at the chemistry now, what you find interesting is the chromium pretty much all goes into the FCC phase here. And so it's probably the FCC phase that's showing the brittle behavior. And this chromium is actually in the fit set. This, by the way, is the 8 atomic percent chromium, which has quite a different microstructure. But it's still FCC and B2. So we did tensile testing. This is the high strain rate where you don't see the environmental embrittlement so much. And as you add different amounts of chromium to the material, you can see the yield strength goes down a little bit until we change that microstructure to 8% chromium. But if you look at the elongation, which is indicated on the right axis, as you add different amounts of chromium, the ductility slowly increases in the material until we change the microstructure. And so what the chromium does is actually improve the ductility of the material. And so what we did was we took the 65% chromium, which is the one that showed the best ductility on the previous slide, and we looked at the 65% chromium doped alloy, and and we tested that as a function of strain rate. And you can see here's the results. So when you add that chromium, not only do you get over this environmental improvement, but you've also improved the ductility of the material as well. So you can see here we get about 17% elongation or so compared to about 10. And we get that roughly at all strain rates. So one of the questions we had was how much chromium do we have to add in order to get this, overcome the environmental improvement? So we did some other tests. These are the tests you saw before, this elongation of failure. This is actually at a slow strain rate, we see the environmental improvement. And so you can see here when we have no chromium, we get variable ductility. If we add chromium, we slowly improve the ductility. And by the time we've added 2% chromium, we're getting about the same ductility as when we do a test at the higher strain range. So by 2% chromium, we've overcome the environmental environment problem, and adding more chromium just adds to the ductility as a whole. So what is the chromium doing? Well, we're not wholly sure, but we did some X-ray photoelectron spectroscopy, and the results are shown here. So in addition to getting aluminum oxide, we were actually forming chromium oxide on the surface. So the chromium oxide is probably competing with the aluminum oxide for oxygen and actually preventing that hydrogen formation. We've looked at this material as a function of temperature, and I just showed the results here. You can see that the material actually has, with chromium, has a yield strength of about 700 MPa over temperature, and that slowly decreases with the increase in temperature. But if you compare this to something like a 304 stainless steel, then it's actually stronger at all those temperatures. So one of the things we did was vary the aluminum content of the alloy. So these are lower aluminum contents than before. And as you decrease the aluminum content, the lamellar spacing changes. So this is with 13 aluminum. Now we've got much more of the FCC phase, and the B2 phase is much thinner lamellae. And so we looked at mechanical properties as we change the aluminum content. So this is the alloy we talked about before with 15 aluminum, and these are low amounts of aluminum. Also, some of the manganese has changed as well. And as we lower the aluminum content in the alloy, these are still two-phase, the yield strength goes down, but the ductility increases. These two are over here where we've decreased the aluminum down to 12% or 11%. And in these cases, actually, yield strength is quite low, but lots of ductility. But these are single-phase materials. So if we actually just look at the two-phase materials we've got, there's actually a very clear correlation between the yield strength and the elongation. So as you increase the or decrease the yield strength, the elongation goes up in the alloy. So there's a clear trade-off between the two. And in fact, you can plot the elongation and the yield strength as a function of volume fraction, the interlamellar spacing for -1/2, or the interlamellar spacing for -1. And actually, the range of values here is such that you really can't tell the difference between those two different functionalizations very well. We also looked at this material as a function of temperature, and you can see that when we reduce the aluminum content, the yield strength is lower at all temperatures than the 15, up to about 800 Kelvin, above which it actually turns out to be just slightly stronger. But again, it's actually stronger than stainless steel at all temperatures. One of the interesting things is when we test at high temperature, remember we had a B2 lamellae and FCC lamellae. When we do the test at high temperature, we also get precipitation in the FCC phase, and these precipitates turn out to be B2 precipitates that are forming the material, and you can see them again here. So this is a common feature of this alloy. So one of the things we've done is a thermomechanical treatment of this alloy as well. So we took this is the initial microstructure, and this is an alloy which we've added chromium to. So this is the initial alloy we've added chromium. And we cold roll it, and this is what it looks like after cold rolling. So we've got an alignment of the lamellar structure, and then we anneal it, so we crystallize it. And after recrystallization, we now get this sort of microstructure. And what this consists of is actually equiax grains of a B2 phase and an FCC phase. And in fact, if we look at the chemistry of those two, so this is the as-cast FCC and B2, and this is the cold worked and annealed, so crystallized FCC and B2. There's actually very little difference in the chemistry between the phases before and afterwards. And if you look at the mechanical properties, so this is the yield strength, so the stress is a function of strain. So you can see the cold work material has a much higher yield strength, with very little ductility. And after we cold roll it and annealed it, it's actually a very little difference from the as-cast material. And the reason for that is that although we've formed a different microstructure, the spacing of the lamellae in the as-cast material was about the same as the grain size is in the recrystallized microstructure. So given the same strength and effect. And when we could get to higher strains in this material with the chromium, what we found was that although we get initial decimation in the FCC phase, later on we get decimation in the B2 phase as well. So the way this material deforms is initially the FCC phase, which is much softer, deforms. And as the FCC phase work hardens, eventually the flow stress in the FCC phase equals the yield strength in the B2 phase, and at which point the B2 phase also starts to deform. So we've also looked at modifying the microstructure by adding different materials. So one thing we did was add titanium. This is material without titanium. Once we added the titanium, we ended up with a much finer microstructure, as seen here in these scanning electron micrographs. But if we actually look at the X-ray diffraction, we've still simply got FCC and B2 phases in all cases. And if we look at what happens to the lattice parameter as a function of titanium, what you see interesting is that FCC lattice parameter doesn't change, but the B2 lattice parameter increases linearly with increasing titanium, which suggests that the titanium largely goes into the B2 phase of the material. And when we look in the TEM here, and we look at the chemistry of the FCC phase and the B2, you can see the titanium is largely in the B2, and there's very little in the FCC phase in the material. So if we look at the mechanical properties, this is the material with no titanium, and then as we add more mass in the titanium, the yield strength goes up, but the ductility goes down. So again, there's a trade-off between ductility and strength, and that's plotted here. You can see the yield strength it plotted as both the insular spacing to -1/2 and to -1. They're fairly similar. It's hard to tell the difference between them. So we also looked at adding carbon to this material because the carbon turned out to be really great strengthening for that single phase ally. Interesting, when we added carbon to this material, a completely different thing happened. So this is the undoped material where we've got these lamellar structures. Once we added carbon, we completely did away with the lamellar structure, and we got these islands of precipitates in material. When we annealed both the undoped and the carbon doped, eventually what we got was this precipitation of this second phase that you saw before. This is the same second phase, it's just a B2 phase that we saw before after tensile testing at higher temperature. So this is a higher magnification. So this is the undoped, the initial original lamellae, and then after we anneal it, you can see all more B2 phase forming here. This is the carbon doped, where we've got this B2 phase forming in the matrix, and we've also got some other precipitates forming within these particles themselves. So it turns out that this adding carbon, we ended up with a 3-phase microstructure of a matrix of FCC-B2, some particles in there, which also themselves have particles in them. And if we look at what those particles are in the carbon doped material, you can see we've actually got a B2 phase, and it turns out we've got a body-centered tetragonal. And you can see that in the TEM. So this is one of those particles in the carbon doped material, and the matrix here is B2, but this stuff inside is all body-centered tetragonal. It's a Martensite. And you can see that if you look at the chemistry, then the matrix has high concentrations of manganese and iron, whereas the Martensite has a lot of nickel and aluminum in it, and so do the B2 precipitates as well. So this shows the yield strength as a function of the heat treatments that I showed in microstructures for before. So the ASCAS materials, with and without carbon, surprisingly have very similar yield strengths. This is all the data up here, just summarizing these graphs. As we heat treat it for an hour at 1000, the strength goes up because we're now producing those extra precipitates in the matrix. And as we anneal it further, we get more precipitation in the matrix, and so the strength goes up. But unfortunately, the ductility goes down pretty much, particularly in the carbon doped material. And this just shows the dislocation structures after very large strains. And again, we get microbands in the FCC phase in this material. So another thing we've done is actually nitride the material. So this is, we did this to both the chromium doped material and without chromium. And this is after we've nitrided the material. So this is at the center of the specimen where nothing much has changed. We've got this similar structure. But near the surface, we've actually got quite a different microstructure. We've got these dark particles, which if you do EDS on, turn out to be aluminum nitride. And if you look at the matrix between those particles, there's actually no aluminum. So the nitride basically sucks all the aluminum out of the matrix and forms these nitrides. So this is the chromium doped material, and this is the material without chromium. Again, you can see the aluminum nitrides. And what that does to mechanical properties, so in the center of the specimen, we get a hardness that looks like this, and at the surface, we get a much greater hardness in the material. So you can actually case harden these materials by nitriding them. And so the last couple of things I just wanted to mention is just a couple of very preliminary studies we've done. So because we have these materials and they look a bit like stainless steels, we decided to compare the corrosion to that of stainless steels. So the top images here are some very crude experiments that I did, where we just took stainless steel, the single-phase high-entropy alloy, and the two-phase high-entropy alloy with chromium, and we put them just in a solution of instant ocean. And what instant ocean is, if you've got a fish tank where you've got some fish from the ocean, then you can buy this stuff, this instant ocean, put into water, and it basically replicates what's in the ocean, the chemistry of the ocean. And you can see that I just let the water evaporate from these, and you can see the high entropy alloy has hardly gone rusty at all, whereas the stainless steel has got a tremendous amount of rust, and all this brown here is the corrosion products. This is a little unfair test on cracked stainless steel because stainless steel is well known to not be known to be susceptible to chloride attack. We did a little bit more sophisticated study where we looked at the corrosion currents for these different materials, and you can see that the stainless steel has a much higher corrosion current than the single-phase high-entropy alloy, and the two-phase high-entropy alloy is actually better still, so it actually shows the best corrosion properties of the material. The other thing that we've done is actually look at oxidizing the material, and so this is the material before oxidation. This is after we've oxidized it, and we looked at the composition of the oxide on the surface, and a lot of the oxide is actually mostly a manganese oxide with little bits of other elements in there as well. And why we're interested in this is for concentrated solar power. So for concentrated solar power, you need to absorb sunlight, and so we measured the optical absorbance over a wide range. So this is beyond the optical spectrum here. And the interesting thing is that oxide on the surface actually absorbs greater than 90% of light over this whole spectrum here, which is very high value actually. And it also has a pretty low emittance as well. So there's great interest in this, and we're actually working on a project on concentrated solar power, where we're looking at these high entropy alloys as tubing materials for concentrated solar power applications. So let me summarize all the work that we've done on the eutectic alloys, and then I can answer questions from people. So we've got these iron, nickel, manganese, aluminum eutectic alloys, which turn out to be FCC and B2. When you deform them, initially the FCC phase forms. As it hardens, later the B2 phase will also deform. The yield strength we get for this material is about 800 MPa with about 9% elongation, but it shows this environmental embrittlement effect So you can add chromium to it. Chromium larger goes into the FCC phase, doesn't really change the microstructure very much. It lowers the yield strength, but actually roughly doubles the elongation failure, and it overcomes this environmental improvement. We looked at varying the aluminum content, and as the aluminum content goes down, the lamellar spacing goes up, and so the yield strength goes down, and the ductility goes up. We looked at cold rolling these materials and annealing them to be crystallized, and we ended up with an equiaxed FCC plus B2 grain structure, which actually had a very similar yield strength and elongation failure to the material started out with. We looked at adding titanium to this material, and titanium increased the yield strength, and this is actually compared to the material that had a yield strength of about 300 MPa. So tremendously increased the yield strength, but unfortunately the ductility dropped really dramatically. And again, this is because the lamellar spacing decreased quite dramatically. We added carbon to the material, and carbon actually completely changes the microstructure, so we don't get lamellae. After annealing, we get D2 particles. And actually, carbon doped material has both good yield strength and good elongation failure after annealing. So we looked at nitriding the material, and nitriding essentially removes all the aluminum from the surface and produces aluminum nitride, so increases the surface hardness. So we've actually shown that we've got excellent corrosion resistance, better than stainless steel, and we've actually got strong rock absorption over the whole spectrum. So with that, I'll finish and answer any questions that have come up.
Thank you so much, Dr. Becker, for this excellent talk. If you have some question, you can write it in the chat, or well, you can turn on your microphone and you can ask directly to Dr. Becker. So for this moment, we have some questions in the chat. Doctor, I will read for you. The first is, can you describe a few more about the strengthening mechanisms in terms of dislocation behavior for obtaining a good relation between mechanical resistance and ductility in high entropy alloys, please?
Well, actually, the high entropy alloys that we're looking at, I think it's mainly just the single phase high entropy alloy. It's mainly just the solute strengthening, and the interstitial solute strengthening is really the big strengthening effect in that alloy. In the two phase alloy, really there you've got a dislocation pilots in the FCC phase at the B2 interface. And so that's why as you decrease the lamellar spacing, the yield strength goes up. So you've simply got a pilot mechanism, a sort of Hall-Petch relationship, but with, instead of grain size, the lamellar spacing. But with a relatively small range of lamellar spacing we've looked at, that's what I was trying to point out, is that it's hard to tell whether it's a lamellar spacing to the power -1 or to the power -1/2.
Thank you so much, Doctor. We have one more question. Is the stress-strain graphs of your slide 68 appear with some multiple minimum and maximum of stress, like in homogeneous deformation? Can you describe this phenomenon a few more, please? This it's in the 68, slide 68.
That would take me a little while to get back to it.
Thank you.
Oh, this one? This is 68.
68, yes, is this. Yes, it say that appear with multiple minimum and maximum of stress, like in heterogeneous deformation. If you can describe a few this phenomenon, please.
Could you repeat the question again? I'm not sure I understand that.
Yeah, sure. I suppose that it say that it appeared with multiple minimum and maximum of stress. I suppose it's related that in the graphs is showing like some, how can I say, like divergency, like some jumps. I suppose it's because of that.
Oh, you mean this thing here?
Yes.
Yeah, I'm actually not quite sure. These are room temperature tests, and yeah, we haven't actually seen that a lot. That mostly occurs at a little higher temperature. You know, probably again due to some impurities in the material. So I'm not quite sure what the cause of that is actually.
Okay, doctor, thank you so much. I think for this moment, we don't have more questions in the chat. If some of you, if some of the attendees would like to open the microphone and ask something directly to Dr. Becker, it's okay. Okay, I think, yes, doctor.
I would just like to mention, if anybody's interested, that a book came out a couple of years ago about different materials that you may be interested in.
Yes, thank you so much, doctor. Yes, also, if you would like to share some of your papers with us, if you wish, you can send to the email of the student chapter, and we will surely share with all the attendees. And I also would like to ask you something related to the corrosion resistance. How you explain that the corrosion resistance improve in high entropy alloys, because these alloys have more precipitates? So the precipitates are, for diverse authors in literature, are mentioned like a stress concentrator, and the stress concentrator are usually points with more reactivity. So usually the corrosion and some chemical process start in that points. So how you describe the mechanisms to improve the corrosion resistance in this kind of alloys?
Actually, I should say I am not an expert on corrosion at all. I did these things by just simply sticking some specimens in solution. One of our other faculty members here actually had one of their graduate students do these actual measurements here. They're a corrosion expert. So I really don't know the answer to your question. And as I mentioned before, the comparison with stainless steel is because we put this in this material instant ocean, this has chlorides in, so would attack, you know, stainless steel is not good in a chloride environment. So I think that's a good question, actually. This single phase alloy is actually worse than the two-phase alloy, which is sort of interesting. So this is sort of backwards from what you might think, actually. This is a B2 and FCC, and this is just FCC. And this has higher aluminum, but they both have similar levels of chromium. So I don't know the answer to that question. I mean, it's quite intriguing. I mean, I think it's very exciting that these materials actually have such good corrosion resistance, but I am not an expert on corrosion at all, actually. So I'm sorry I can't answer that anymore.
Don't worry, doctor. It's very interesting phenomenon.
It is actually something we're pursuing because we're looking at these materials as for some biomedical applications as well, as possible replacements like rods or plates that are put into people. And of course, stainless steels have some issues with them in those environments. And so we're actually looking at corrosion in sort of some solutions that replicate bodily fluids to see how they corrode in those environments.